Hello guys, welcome back to my channel. And in this video, we're going to be tackling integrals of the Dilogarithm function, because in the very last video, we dealt with proving some identities of the Dilogarithm function. So I said to myself, let's cook up a nice Dilogarithm integral and let's evaluate that in this video. So as always, let's get started. Okay, so to start with today, let's call whatever the integral we are going to have I. That's defined as integral from 0 to 1 of the dilogarithm of z dz. Okay, okay. Uh, at first this might not look bad, but if you insist on using the dilogarithm integral representation, then it's going to be integral from 0 to z of natural log of 1 minus t over t dt. And now you're actually seeing the ugly part of it. So option number one, you could go forward with changing the coordinates to polar coordinates, because this is a double integral. Best way to calculate some of these is to convert to polar coordinates. But option number two is I call the classy method. Okay, let's face the fact, polar coordinates might work, might not work, I don't know, I don't care. And it's it's still going to be horrible, it's going to look horrible in any case. Any method you choose, it's going to be some uh, work that you need to do before you actually come to a conclusive answer. So I mean, the journey is going to be messy in both options. Why not go with the classy option? Because this integral is still perfectly horrid whatever you do. So let's be classy with it. I hope you get why we need to be a little classy this time. Okay, so with that being said, option number one was out of question. So forget expanding this out in terms of a double integral. What we are actually going to do is use symmetry. At first, it may not make sense why I'm doing this, but for those of you who've watched yesterday's video, will know why I'm doing this. So for using symmetry, say if you have integral from say a to b f of x dx, that is going to be equal to integral from a to b of f of b plus a minus x dx. Upper bound plus lower bound minus x. So if we use this fact on this dilogarithm, we'll have dilogarithm of 1 plus 0, which is 1, minus z dz, and that's still I, that's still the same integral. Now what I'm going to do is I'm going to add this equation number 1 and equation number 2. So adding 1 and 2, we come to the conclusion that 2 times I is equal to integral from 0 to 1 of dilogarithm of z plus dilogarithm of 1 minus z dz. Fair enough. Now at this point, those of you who haven't seen yesterday's video, please watch it, because what is going to follow is actually yesterday's reflection formula for the logarithm function. So the reflection formula said the logarithm of z plus the logarithm of 1 minus z is actually equal to pi squared over 6 minus the logarithm of z times the natural log of z times the natural log of 1 minus z. That's the entire identity that we're going to use, the reflection formula. And in case you want a proof of this, yesterday's video, please. So then going forward with our plan of using this identity, we have the integral from 0 to 1 of pi squared over 6 minus natural log of z times natural log of 1 minus z dz. So we can basically use linearity, split this up into pi squared over 6 integral from 0 to 1 of dx minus integral integral from 0 to 1 of natural log of z times natural log of 1 minus z dz. Well, this first integral is just going to be pi squared over 6, because it will be z evaluated from 0 to 1, which will just be 1, minus, now noticing this second natural log over here, it looks, it's almost calling out to us to use the Taylor series. So I'm going to use just that, sum from k equals 1 to infinity minus 1 to the k plus 1 over k, because there is literally no other elementary technique we can use apart from integration by parts, but that's not really a good idea here. So we have natural log of z and negative z to the kth power dz, which becomes pi squared over 6 minus, assuming uniform and absolute convergence, summation comes outside, integral from 0 to k equals 1 to infinity of minus 1 to the k plus 1 multiplied with minus 1 to the k divided by k, integral from 0 to 1 of natural log of z times z to the k dz. So minus 1 to the k minus 1 to the k will make minus 1 to the 2k, and negative 1 having an even power will just become 1. So this negative and this negative will cancel out to give us a positive sum from k equals 1 to infinity of 1 over k integral from 0 to 1 natural log of z to the k dz. Now it's actually a good time to use integration by parts, and as you might have suspected, we are going to be integrating the z to the k and differentiating the natural log. So we basically have natural log of z over k plus 1 times z to the k plus 1 evaluated from 0 to 1 minus integral from 0 to 1 of k plus 1 still in the denominator. We have z to the k plus 1, but then we are going to divide because of the derivative of the natural log dz, like that. So it's pi squared over 6 plus sum from k equals 1 to infinity of 1 over k times k plus 1, and we have natural log of z to the k plus 1 evaluated from 0 to 1 minus integral from 0 to 1 of z to the k dz, because we took the k plus 1 outside commonly. So when you plug in 1, natural log of 1 times 1, natural log of 1 is 0, so you'll have 0. And then when you plug in 0, you'll have a 0 times negative infinity situation. Natural log of 0 tends to negative infinity. And once you do all that L'Hopital mess and whatever, I mean, it's basically going to be natural log of z times z to the negative k negative 1. And then when you say apply L'Hopital's rule, in the limit that z goes to 0, you apply L'Hopital's rule, you're going to have a 1 over z times z to the negative k negative 1, the limit that z goes to 0. So one of these cancels out. You basically limit as z goes to 0 of z to the k, which is officially 0. So that's why we have 0 even for the lower bound, making this entire thing go to 0. So finally we have pi squared over 6 plus sum from k equals 1 to infinity of, well, antiderivative of this is pretty easy to calculate. Z to the k plus 1 over k plus 1 evaluated from 0 to 1. And yeah, there's a negative also, because there was a negative here. So when you plug in 1, you'll just have 1, and then for 0 you have a 0. So pi squared over 6 minus sum from k equals 1 to infinity of 1 over k times k plus 1 squared. And I'm going to call this thing excluding the negative s. So 2 times I is officially pi squared over 6 minus s. And as you might have suspected already, I'm going to tackle s on a fresh page. So see you there. So as previously discussed, s is actually sum from k equals 1 to infinity of 1 over k times k plus 1 squared. So now, noticing that the product of uh, factors in the denominator is actually telling us to use partial fraction decomposition. So this means 1 over k times k plus 1 squared, forget the sum for now, is equal to a, some constant over k, plus b over k plus 1 plus c over k plus 1 squared. And if you're asking me why we're writing this denominator, which was originally squared, in terms of increasing powers of the same, well, that's because of the basic principles of partial fraction decomposition. So if you're like blank now about what I did, what I'm saying, please revise your partial fraction decomposition. I could make a video. Again, you could request me in the comment section. So now cross multiplying and getting rid of the denominator, we have a times k plus 1 squared plus b times k plus 1 plus c times k. So 1 is equal to, now expanding the bracket, ak squared plus 2ak plus a plus bk squared plus b plus ck. So gathering terms which have basically the same polynomial parts, a plus b come under k squared, got rid of them. Then with k come these terms of 2a plus b plus c. Um, so well, yeah, got rid of them. And then the constant term is just a. So you know that what that means? That means that a is equal to 1, a plus b is equal to 0, but since a is 1, b has to be negative 1. We know 2a plus b plus c is 0. Substitute whatever we know in. So we have 2 times 1, which is 2, minus 1 for the b, plus c is equal to 0, and means that c is equal to negative 1. So a is 1, b is negative 1, c is negative 1. So what that does to s is instead of having sum from k equals 1 to infinity of 1 over k times k plus 1 squared, what we end up actually uh, with is sum from k equals 1 to infinity of 1 over k minus 1 over k plus 1 minus sum from k equals 1 to infinity of 1 over k plus 1, but the whole thing squared. Now I'm actually wanting to group both of these terms together because separately these two will diverge. They'll become harmonic series basically. So let me just write some of these terms. So for k equals 1, we have 1 over 1 minus 1 over 2, and then half minus 1 over 3, and that goes on. And the last terms we have is 1 over k minus 1 over k plus 1. Again, because it's an infinite sum, we need to take the limit as that last term k goes to infinity. So notice it's an alternating series. This cancels out with this will cancel out with the next term, this will cancel out with the term before it, just ending up us with a limit as k goes to infinity of 1 minus 1 over k plus 1. Well, in the limit that k goes to infinity, this will just go to 0, just giving us 1. So this entire thing will telescope to 1. It's a telescoping series. So our s now becomes 1 minus, let's write out some terms of this. So we have 1 over 2 squared plus 1 over 3 squared plus, well, dot 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 infinity. Okay, and notice this is almost like the Riemann zeta function, except we're missing the first term, which is 1 over 1 squared. So why don't add that? 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, going on till infinity. But uh, don't forget to subtract the 1 over 1 squared again, because originally it wasn't there, we just introduced it on our own. So what that does is this just becomes the Riemann zeta of 2 minus 1. So we have 1 plus 1 minus Riemann zeta of 2, which is 2 minus the Riemann zeta of 2. The Riemann zeta of 2 is actually the famous Bessel problem, and I promise I will do a comprehensive proof and an elementary proof of this. 2 minus pi squared over 6. That's basically what your sum s is equal to. Now it's actually time to plug this back into our original integral I, or rather 2i. So finally the general equation we had was 2i is equal to essentially pi squared over 6 minus s. And we know what s turned out to be, don't we? 2 minus pi squared over 6, and that will become pi squared over 6 plus pi squared over 6 minus 2, which basically turns out to be pi squared over 3 minus 2, and that is 2i. So why not divide both sides by 2? So these two cancel out. So I is nothing but pi squared over 6 minus 2 over 2, which is 1. Fair enough. But again, just to conclude stuff that was going on from the start, I was equal to integral from 0 to 1 of the dilogarithm of z dz. And I'm writing z instead of x because the dilogarithm can take any complex arguments as well. Turns out to be pi squared over 6 minus 1, which has an approximate value of 0.644934. Isn't that great? So however horrendous it was, we came out with this nice answer using the reflection formula and then evaluating this sum separately. Again, using the fact that this pi squared over 6 actually came from the Riemann zeta of 2. But in any case, we've solved the problem. Isn't that a nice result for something like the dilogarithm? I mean, you can try doing this with the double integral method, using the integral definition of the dilogarithm of z, and then using polar coordinates, or I don't know, switching integrals, or like, I really don't know. You could also use Stokes theorem, or I don't care. But if you get an answer using the other methods, the same answer, you can write in the comment section what you got and how was the process, and enlighten us. So I think that's it for this video, guys. I hope you enjoyed it. I hope you learned a lot. Now, before going, please like, share, and subscribe to my channel. Recommend me to your friends. Spread the word of Gamma Di Gamma in the math community. And in the meantime, stay home, stay safe, keep doing math, don't get bored, take care of yourselves, and peace out. Stay tuned for more content from Gamma Di Gamma. Signing out.